Hey guys! So during our last meeting, we have started with this topic, trigonometric substitution, and I believe that we were able to cover the first item in here. So this time, in this video, we will be covering the rest of this slide sets. So let's get started. Let us again recall what identities that we will be using a lot of times in this technique. So we got the Pythagorean identities. We have sine squared theta equals 1 minus cosine squared theta. Tangent squared theta equals secant squared theta minus 1. And secant squared theta equals 1 plus tangent squared theta. So since we'll be doing the second and the third items, um, most of the time we'll be using the second and third identities. Okay, let us also recall the SOHCAHTOA. So if you got a triangle, right triangle to be more precise, and this is the angle theta, then the side opposite of angle theta, let's just label that as O. The side adjacent to the theta, let us just label that as H. And the hypotenuse, of course, we label that as H. And here we have the SOHCAHTOA. So it only means that here we have sine of theta. Sine of theta, this is equal to the opposite side over the hypotenuse. So sine of theta equals the opposite side over the hypotenuse. So that's our SO. Cosine theta equals the adjacent side over the hypotenuse. So cosine theta, adjacent side, hypotenuse. So ka, so cosine theta, adjacent side, hypotenuse. And finally, we got the TOA. Tangent theta equals opposite side over the adjacent. So tangent theta equals opposite side over adjacent. TOA. Okay, so this is our SOHCAHTOA. So if if necessary, you can use this one, or if not, you can use identities, trigonometric identities, if you still remember them. And a lot of times, some of the trigonometric values, they are already in your computation. Okay, so now let us proceed to our next form. Is it this one here? Okay, so our form now will be uh, the form a squared plus u squared. So again, in here we will assume that our a is greater than 0 and u is some function. So it could be a simple function u equals x, but in some of the examples that we will see later, the u may be other functions, other type of functions. So if we see this form, a squared plus u squared, our substitution will be u equals a tangent theta. And in here, theta will be in this interval, negative pi over 2, comma pi over 2. In the circle, this is actually your fourth quadrant and first quadrant. And we require, at least with this restriction of theta, we need the fourth quadrant and the first quadrant so that when we take the square root of what's inside after the substitution, we don't have to worry about putting absolute values. So anyway, let us consider this example. So in here, we want to integrate square root of 4 plus x squared dx. So in here, our a is equal to 2, and our u, which is just x. So let us just write x equals 2 tangent theta. So if we calculate this, we have x squared equals 4 tangent squared theta. And if we add 4 on both sides, 4 plus x squared, this will be 4 plus 4 tangent squared theta. And we can factor out 4. We will have 4 times 1 plus tangent squared theta, and 1 plus tangent squared theta, that is equal to secant squared theta. So this is what I'm saying. If we take the square root of 4 plus x squared, this will be equal to the square root of 4 secant squared theta. Secant squared theta, it has a variable. So if you got the square root of a variable squared, by definition, you have to take the absolute values. Okay? So in here, if you have x squared and then you take the square root of this should be equal to absolute value of x because we don't know what x is. Is it positive or is it negative? Now, since our theta is in this interval, it means that the theta is in the fourth quadrant or first quadrant, and the values of secant in the fourth quadrant and first quadrant are positive. So since we know that the value of secant is always positive in that restriction, then we can just write this as 2 secant theta. So we don't have to put the absolute value. So that's the point of putting this restriction. Okay? Now let us proceed. We have the square root of 4 plus x squared. We want the dx, but the dx will come from this one. Dx equals 2 secant squared theta, which means that this integral now can be written as the integral of 2 secant theta. The dx is 2 secant squared theta d theta. Oops, I forgot to put d theta in here. Or this one here is, well, we have 2 times 2, that's equal to 4. We bring it outside the integral symbol. And we got here secant cube theta d theta. So from here, you can use your reduction formula. Okay? If not, well, you can derive. If you don't remember your reduction formula, you can derive the formula itself. Or you can integrate directly your secant cube theta. So let us just show that secant cube theta. So let us put an aside in here. Integral of secant cube theta d theta. So this will be, we can write this as integral of secant theta times secant squared theta d theta. And then you can use integration by parts. You can let u equals secant theta dv equals secant squared theta d theta. Du will be equal to secant theta tangent theta d theta, and v equals tangent theta. So with that integration by parts, we have uv, we have the secant theta tangent theta minus integral of v du. So we have v and then this is the du. So if we multiply that, we will have secant theta tangent squared theta d theta. And then from here, we copy the first part. The second part, we change tangent squared theta into secant. So in here, we will have secant theta times the identity will be secant squared theta minus 1 d theta. Then we can distribute. So this one will become secant theta tangent theta minus integral of secant cube theta d theta. And then we got here minus and minus, so that becomes plus integral of secant theta d theta. And then for this one, we bring it to the other side. We bring it to the other side of the equation. So the other side of the equation will become 2 integral of secant cube theta d theta. So in here, we will have 2 integral of secant cube theta d theta. This will be equal to secant theta tangent theta. And then the integral of secant theta, that's just ln absolute value of secant theta plus tangent theta. And then you got your plus some constant, say c sub 1. And then we divide everything by 2, and we will have the integral of secant cube theta. Which means that in here, we will have 4 times, we got 1/2 times secant theta tangent theta plus ln absolute value of secant theta plus tangent theta. And then let's just put the plus c outside. Then you can multiply the 4 and you will just have 2 as a coefficient of everything. If we do that, you will have your 2. You will have 2 times secant theta tangent theta plus ln absolute value of secant theta plus tangent theta, and then we got plus c. And now we bring back the x's or the x. We got secant theta and tangent theta, secant theta and tangent theta. Tangent theta can be obtained from here. Your secant theta, you can actually use this part here. So if we do that, this one here, you will have tangent theta equals x over 2. And then from here, your secant theta equals 4 plus x squared. You take the square root of this, and then you divide by 2. And therefore, the final answer will be 2 times secant theta. It's 4 plus x squared. Square root of that, you divide by 2. Your tangent theta is x over 2 plus you have ln absolute value of 4 plus x squared. You take the square root of that, divided by 2 plus x over 2, and then the plus c. You can distribute these 2 here and cancel one of this, and then this one, attach it as a coefficient in here, or you can just keep that as the final answer. So this will be our final answer. Okay, so that's one example for this form. Let us consider another example here. So in here, you notice particularly this one here, you got 9x squared. But 9x squared can be written as 3x quantity squared. So this is your 9x squared, which means this one here, this is your u. So 3x equals a tangent theta. Your this is equal to 4. So this means that your 3x, this is equal to 4 tangent theta. Then as usual, you square both sides, you got 9x squared on the left hand side, and then on the right hand side, 16 tangent squared theta. So if we add 16 both sides of the equation, we got 16 plus 9x squared. This will be 16 plus 16 tangent squared theta. And then you can factor out 16, and eventually you'll just have 16 secant squared theta. So we can skip that part. Okay? And if you take the square root, you'll have square root of 16 plus 9x squared. This will be 4 secant theta. So this one here is done. For the x squared, you can get it from here. You just divide everything by 9. And then, of course, the dx from here, we will have 3 dx equals 4 secant squared theta d theta, and you divide by 3. So, let us now rewrite the integral as follows. So, square root of 16 plus 9x squared, that's 4 secant theta. Dx, let me just write the dx right here. Dx will be 4 over 3 secant squared theta d theta. For the x squared, we get 16 over 9 tangent squared theta. So again, that came from this one here. Your x squared equals 16 divided by 9 tangent squared theta. Then we can simplify everything, particularly the constants. This, and this, they will cancel each other, while this one and this one will be left with 3 on the denominator. So from here, we can put the 3 in the numerator because it is the denominator of the denominator. So it becomes a numerator. And then you will get integral of secant squared theta, tangent squared theta. Now you can combine secant theta and secant squared theta into secant cubed theta, but there is a tangent squared theta on the denominator. The power of if you do that, the power of secant is odd, and the power of tangent will be even. Because if you bring this in the numerator, the power of tangent will be -2. So it's still even. But we cannot work on that. I mean, the first two techniques in our trigonometric integrals cannot be used. So we will we will try to simplify this expression so that this can be integrated easily. One way to do that is to convert everything in terms of sine and cosine and manipulate. You can work on that. You can try that method. But for this discussion, I will not do that. What I'm gonna do is to convert secant squared theta into tangent squared theta plus 1. So what we will have in the numerator is secant theta times tangent squared theta plus 1, and then we got the d theta, and the denominator will be tangent squared theta. Then we can distribute secant theta. We will have 3 integral of secant theta tangent squared theta plus secant theta. Everything divided by tangent squared theta, and then we got the d theta. Then we can separate. We can separate the numerator, and we will get the integral, or 3 times the integral of secant theta d theta. That's easily integrable. And then plus 3 times the integral of secant theta over tangent squared theta d theta. And then this part here, this is the one that we will convert to in terms of sine and cosine and simplify what we can simplify. So for the first part, first we have 3 integral of secant theta. That's ln absolute value of secant theta plus tangent theta. For the second part, let us rewrite it as the integral of secant theta times cotangent squared theta d theta. Then let us simplify this one. Let us convert this one into in terms of sine and cosine. We will have here 3 ln absolute value of secant theta plus tangent theta plus 3 integral secant theta is 1 over cosine theta. Cotangent theta is cosine theta over sine theta. So this will be cosine squared theta divided by sine squared theta d theta. And in here, this will cancel one of the cosines in the numerator. So what we will get is the following. We will have here 3 ln absolute value of secant theta plus tangent theta. And then for the other one, we will have 3 cosine theta. Let us look at this particular expression here. Your cosine theta, let me write it somewhere on the side. Cosine theta over sine squared theta, you can write this as cosine theta over sine theta times 1 over sine theta. But cosine theta over sine theta, that's equal to cotangent theta. And 1 over sine theta, that's cosecant theta. Which means the integral simplifies into cosecant theta, cotangent theta, d theta. And this part here is easily integrable. This is negative cosecant theta after integrating. So we will have 3 ln absolute value of secant theta plus tangent theta. Now let me write it in the other page. Dot, dot, dot. Let's see. So equals dot, dot, dot equals, we have this one here. So we will have 3 ln absolute value of secant theta plus tangent theta plus 3, or minus actually, becomes minus 3 cosecant theta plus c. Okay, and let us go back to the previous page, because we will need this part here. 3x equals 4 tangent theta. To get tangent theta, we also need this part here. 4 secant theta equals square root of 16 plus 9x squared. So we will get your secant theta. Let me write it on the other side. We will have your secant theta. This is 16 plus 9x squared divided by 3. Or divided by 4. Let me check that again. Yep, it's divided by 4. And then for the tangent theta, we have 3x divided by 4. So if we look at this, we got the triangle TOA. This is your 3x, this is 4, and this will be 16 plus 9x squared. Sine theta is so opposite, which is 3x divided by square root of 16 plus 9x squared, which means cosecant theta is the reciprocal of this. Therefore, we will have 3 ln absolute value of 16 plus 9x squared divided by, oh, you take the square root of that, divided by 4 plus 3x over 4 minus 3. For the cosecant, we will have 16 plus 9x squared. We take the square root of that, and then divided by 3x. And then finally, the plus c. So this is the final answer for this problem. Okay? Okay. So that's for the form a squared plus u squared. Let us now move on to the next form. We got here u squared minus a squared. If you see this, if you notice, you got u squared minus a squared. The first form, it's a squared minus u squared. So the subtrahend in the first form is a function squared, while in here, the subtrahend is the constant. And of course, if you check the second form, a squared plus u squared, it is the same as u squared plus a squared. So we don't have to flip or to exchange the positions of your a squared and u squared. For this one and this one, they are important. The positioning of the constant squared and the function squared um, is important. So in here, if we got the form function squared minus a squared, our substitution is a secant theta, where your theta is in this interval or union of intervals 0 to pi over 2 union pi comma 3 pi over 2. If you check this in your circle, this one here is first quadrant. This one here is third quadrant. So it is important that we take the first quadrant and the third quadrant. The reason is, if we take the square root of u squared minus a squared, well, particularly if you have u squared minus a squared, that will become tangent squared, or some sort of tangent squared times a constant. If you take the square root of tangent squared, then you will need to put absolute value of tangent theta. Now, we can remove the absolute value knowing that our theta is in the first quadrant and third quadrant. Remember that in the first quadrant and third quadrant, theta or tangent theta is positive. So we know that the one inside here is positive. I mean the something squared. The something is positive. So if we take the square root of that, we don't have to put the absolute value. Okay? So the restrictions are there. So we know that we can just um, take the square root of a squared and just put, or take the square root of u squared or whatever, and just remove the absolute value. So a lot of times these intervals, the restrictions in the intervals, the restrictions of your theta, they are taken for granted, but they are there to simplify our computation. So anyway, let us consider this example. Here, we got here integral of dx over square root of x squared minus 9 dx. So there is an excess of this dx, so let me just remove this one here. We don't need this excess here. Anyway, so we got this integral. So here we just have the simple x again as our u. So x will be, or a first, a will be equal to 3, and x will be equal to 3 secant theta. And x over 3, well, this is equal to secant theta. Anyway, I've written it there. So let's us just keep that for later. But what I want to do actually is to square both sides. We will have 9 secant squared theta. And then we will have x squared minus 9. This will be 9 secant squared theta minus 9. We factor out 9. We will have secant squared theta minus 1 inside the parenthesis. But then again, secant squared minus 1, that's tangent squared. So 9 tangent squared theta. So if we take square root of both sides, x squared minus 9, we take the square root of this will become 3 tangent theta. And again, we don't have to put the absolute value because of the restriction that we gave for theta, that we imposed on theta. And then from here, from this one here, we can find the dx. Dx will be 3 secant theta tangent theta d theta. Therefore, we will have now the integral. The dx, it's 3 secant theta tangent theta d theta. Square root of x squared minus 9, that's 3 tangent theta. And this will cancel this one will cancel this one, and our integral becomes integral of secant theta d theta, and integrating this, we get ln absolute value of secant theta plus tangent theta plus c. Secant theta is from here. Tangent theta, we can get it from here. So our final answer will be ln absolute value of x over 3 plus tangent theta, it's x squared minus 9. We take the square root of this divided by 3, and then plus the arbitrary constant c. So this is the final answer. Next item, Ra here, this is equal to 2. Our u is a simple x, so x will become 2 secant theta. Take the square of both sides, we will have x squared equals 4 secant squared theta. Then we subtract 4 on both sides. You will have here 4 secant squared theta minus 4, and we can skip the factoring and then the converting. We'll just have 4 tangent squared theta. We need the square root, so square root of both sides. We will have here 2 tangent theta. From here we got we have dx equals 2 secant theta tangent theta d theta, which means we will have the integral. In the numerator, we have 2 tangent theta. Dx is 2 secant theta tangent theta d theta. Denominator, we got x in here, but x is equal to 2 secant theta. So denominator is 2 secant theta. So this one will cancel this one here. We still have a coefficient 2. Integral of tangent squared theta d theta. The power of tangent is even, and our technique convert everything to in terms of secant. Well, the power of secant here is 0, which is also an even number, but you can use the technique for secant squared, but I think it will be much longer in a sense. So what we're gonna do is just to convert tangent squared theta to in terms of secant squared theta minus 1. So in here you will have 2 integral of secant squared theta minus 1 d theta, integral of secant squared theta, that's tangent theta, minus integral of 1, that's just theta, plus c. Tangent theta will be this one here, or will be coming from this one. For the theta, we use our original substitution, so we can find that one. So from this here, we will have, secant theta equals x over 2, and theta will be secant inverse of x over 2. Which means the final answer will be 2 times tangent theta is x squared minus 4. You take the square root of this, and then we divide by 2, minus secant, minus theta, which is secant inverse of x over 2. And then plus the arbitrary constant c. So again, the only time we will use inverse trig is if we just get a theta. We cannot have, as a final answer, I don't want to see trigonometric of inverse trig times whatever. Meaning, in the arguments of your trigonometric function, we should not see any inverse trig. Okay? So, that covers all the forms. A squared plus u squared minus a squared, and in the previous meeting, we got a squared minus u squared. So for the rest, I'll just do the last set of examples that I have in here, and then one more example. So here we got integral of dx over e to the 2x plus 16 raised to 3 halves. So notice this is of the form u squared plus a squared. Our u here, if you notice, we have here e to the 2x, but e to the 2x can be written as e to the x squared, which means this here is our u. Our a, that will be equal to 4. So here a equals 4, u, which is e to the x, will now become 4 tangent theta. So if we square e to the 2x, we will have 16 tangent squared theta. We had 16 on both sides. We will have 16 plus e to the 2x, or e to the 2x plus 16. We will have 16 plus 16 tangent squared theta. And let us skip the factoring part. This will be secant squared theta. If you raise this to 3 halves, what will we get? We will have 16 plus e to the 2x. You raise this to 3 halves. Take note that 16 is equal to 4 squared. Let me write that 16 as 4 squared. And then we got we still have secant squared theta, and you raise this to 3 halves, and notice that the power 2 will cancel the power half. So if you simplify this, you will have 4 cubed secant cube theta. For the dx, we have it in here. We get the derivative of both sides. We will have e to the x dx. This will be 4 secant squared, oops, oh, yeah, 4 secant squared theta d theta. We have e to the x in here, but e to the x is equal to 4 tangent theta. So if we isolate dx, we will have 4 secant squared theta d theta divided by e to the x, but e to the x is 4 tangent theta. So on the denominator, we have here 4 tangent theta. And of course, the 4 will cancel the 4 in here. So if we substitute now to the original integral, we got here integral dx, that will be secant squared theta over tangent theta d theta. On the denominator, you have here 4 cubed. 4 times 4 is 16, times 4 is 64, so we have 64 in here. Then we have secant cube, secant cube theta. Of course, the 64 will remain in the denominator, so we can bring it out, 1 over 64. And then secant squared divided by secant cube, that's 1 over secant. So if we do that, let us just write it in this way. We will have the integral of 1 over tangent theta, secant theta. Then we have here d theta. So try to manipulate if you can't follow it yet. Try to manipulate this one. Okay. You will end up with the denominator secant theta tangent theta, or tangent theta secant theta. Then to simplify things further, we will have, let us convert everything to in terms of sine and cosine. We will have here integral of, you got d theta. Tangent theta is sine theta over cosine theta. Secant theta is 1 over cosine theta. So this one we can rewrite as integral of, in the numerator you have cosine squared theta. On the denominator you have here sine theta, d theta. So in here, notice cosine squared theta, the power of cosine is even. The denominator is sine theta. If you put it in the numerator, the power will be negative. Correct? The power will be negative 1. And it's an odd number. So you can use the technique for having an odd power for sine and cosine. However, what I'm gonna do here instead of doing that is to convert cosine squared theta into in terms of sine. Cosine squared theta, that's sine squared theta. Oops, no, not sine squared theta, but 1 minus sine squared theta. And of course, you have the denominator sine theta. And then d theta. And then you can separate 1 minus sine squared theta into two parts. So you will have here integral of 1 over sine theta, that becomes cosecant theta. Sine squared over sine, that's just sine. So you have here minus sine theta d theta. Therefore, if we integrate now, integral of cosecant theta, that will be ln cosecant theta minus cotangent theta in absolute values. Then integral of negative sine theta, that's positive cosine theta. And then you have your plus c. So from here, you now have to get cosecant theta, cotangent theta, and cosine theta. Cotangent theta, you can get it directly from this one. Well, not really directly, but at least the reciprocal, you will be able to get the cotangent theta. For cosecant and cosine, we need to manipulate things, but we can just use triangles. So in here, let me put the triangle on this part here. This is theta, and we got the tangent. So TOA, opposite will be e to the x, adjacent will be 4, and this is e to the 2x plus 16. You take the square root of this. So sine theta is e to the x over e to the 2x plus 16. You take the square root. So that cosecant theta is the reciprocal of this one. Cosine theta is adjacent, which is 4 over the hypotenuse. E to the 2x plus 16, and you take the square root of this. Therefore, the final answer will be equals 1 over 64 times ln absolute value e to the 2x plus 16, you take the square root of this over e to the x minus cotangent, that's 4 over e to the x. That's the reciprocal of tangent theta, and tangent theta is coming from here. And then for the cosine, we got here, so plus 4 over e to the 2x plus 16, you take the square root of this, and then plus the arbitrary constant c. No, you close this parenthesis. So this will be the final answer. Let me just use a different color. So that's our final answer. Next item. We want to integrate square root of 4x minus x squared over x dx. Now look at this. Our form is constant squared minus function squared minus constant squared, or constant squared minus function squared, or constant squared plus function squared. But what we have here is something in terms of a function minus something a function, which means we cannot directly apply this form yet. What we can do is to, well, get this form or this form or this form coming from this expression. To do that, we will need our completing the square. Okay, we will need our completing the square. So how do we do that? Try to recall how to do completing the square. You can pause this video if you need to recall how to do it, but I'll proceed anyway. We got 4x minus x squared. What we're gonna do is to add 4 and subtract 4. So in here, we will have 4 minus 4. 4 minus 4, that's equal to 0. And then we have here plus 4x minus x squared. So basically, I just rewrote 4x minus x squared into 4 minus 4 plus 4x minus x squared. So they are equal because 4 minus 4 will cancel. However, we need that 4 minus 4. Okay? Particularly the minus 4. We will combine it to the 4x minus x squared. So what you will see is the following. If we manipulate this equation or expression, we will have 4 minus quantity x squared minus 4x plus 4. So what I did was to factor out the negative from this expression. So if you don't believe it, well, you can distribute the negative and you will end up with this expression, and then you will end up with the original expression. But what is this x squared minus 4x plus 4? This is a perfect square trinomial. That's what happens when you do completing the square. You complete the square. From an expression, if you complete the square, it means you get a perfect square. In this case, x squared minus 4x plus 4 is a perfect square trinomial that can be written as x minus 2 squared. And now, in this, you can see that we got something constant minus a function squared. And it is now of this form. Meaning our a here, this will be equal to 2. Our u, this is equal to x minus 2. Since this is the first form, constant squared minus u squared, we use sign substitution. So what will we get is the following. X minus 2 equals 2 sine theta. Then we proceed, we square. We will have x minus 2 squared. This is 4 sine squared theta. And then we have 4 minus x squared minus, not x squared, but x minus 2 squared. This will be 4 minus 4 sine squared theta. And again, we can skip the factoring part and the conversion part. In the end, you will have 4 cosine squared theta. Take note that this one here is this one, which is exactly, so this one here is this one, which is exactly 4x minus x squared. So if I take the square root of this one, that will be the same as the square root of this one, which is this numerator here. Okay, so again, if I take the square root of this one, that's the same as the square root of this one, which is the numerator in here. Which means that square root of 4 minus x minus 2 squared, this will be 2 cosine theta. So we now have the numerator. From here, dx, derivative of x minus 2 is simply dx. So that's just dx. On the other side, we will have 2 cosine theta d theta. So in here, we will have the integral of 2 cosine theta. And then we have the dx, which is times 2 cosine theta d theta. On the denominator, we have x. We can solve for x from here. Correct. X will be 2 sine theta plus 2. Look at this one. So if we put this to the other side, it becomes plus. Cool. So we have here 2 cosine theta times 2 cosine theta d theta. Or we will have, outside, we will have 2 times 2, that's 4. Inside, in the numerator, we will have here cosine squared theta. On the denominator, we can factor out 2. So we can factor out 2 and bring it out. But the denominator still has sine theta plus 1 d theta. From here, we can do what? We can use some identities and use some techniques if you want to. Take note that this is sine theta plus 1. So you cannot separate it. It's on a denominator. You cannot write this as cosine squared theta over sine theta plus cosine squared theta over 1. You cannot separate addends on the denominator and use the same numerator for both. But the trick here is to convert cosine squared theta. So in here, 4 over 2, that's just 2. In the numerator, you can write it as 1 minus sine squared theta. Denominator is still sine theta plus 1 d theta. Notice that 1 minus sine squared theta, it's a difference of 2 squares. If you remember that, that's a difference of 2 squares, you can write 1 minus sine squared theta as 1 minus sine theta, 1 plus sine theta. And the denominator is sine theta plus 1, and then you have your d theta. And voila, you can cancel 1 plus sine theta plus 1. So this one cancels this one, and the numerator simplifies into 1 minus sine theta d theta. So integrating, you will have 2, integral of 1, that's theta, integral of negative sine theta, that's positive cosine theta. And then you have your plus c. Of course, your theta, since it's just theta, we can use inverse trig. It's coming from this one here. So from this one here, first we need we divide by 2. We will have here x minus 2 over 2 equals sine theta. So theta will be sine inverse of x minus 2 over 2. As for the cosine, we can use triangles again. So let me just write or put the triangle right here. We got the triangle. Sine theta equals x minus 2. So this will be x minus 2. Then over 2, 2 will be the hypotenuse. And if you remember from our last meeting, normally that the missing part is actually the one that we have in here. So you take the square root of that, right? The missing part will be 4 minus quantity x minus 2 squared. Okay? But that one is exactly the same as this one. So the missing part will be square root of 4x minus x squared. Actually, in fact, we can find cosine immediately from here. I just realized that one. So, yeah, we got your sine theta. From here, we will have cosine theta equals, let me write it as square root of 4x minus x squared, and then the denominator will be 2. Right, so the final answer will be 2 times theta, which is sine inverse of x minus 2 over 2, plus cosine theta, that will be 4x minus x squared. You take the square root of this, then divide by 2, and then finally you add the arbitrary constant c. So this will be our final answer. So the trick here is to do your completing the square. Okay, so again, just to emphasize, our forms are constant squared minus function squared, constant squared plus function squared minus constant squared. But in here, inside, we got a function minus a function. So that's the reason why we need to do completing the square. So you will be able to write the expression here in terms of this one. Next example, in here we got dx over square root of x squared plus 6x plus 13. So in here we got something in square, but there's another function in here and there's a constant in here. Okay? But if you notice, we can find a perfect square of some function from this expression. Namely, we will have integral, you got your dx in here. On the denominator, you can write that one as x squared plus 6x plus 9 plus 4. And this expression here is a perfect square trinomial that you can write as, so let's put dx in the numerator. On the denominator, you can write that as you got x plus 3 squared. And of course, there's a plus 4 there, which is what? Square of 2. So now you have here function squared plus some constant. So this is the second form. So we use tangent substitution. Our a, that's equal to 2. Our u is actually x plus 3. And this will be 2 tangent theta. Then again, you square it. X plus 3 squared. This will be 4 tangent squared theta. X plus 3 squared plus 4. This will be 4 tangent squared theta plus 4. And again, we skip the factoring. We'll just write this as 4 secant squared theta. You take the square root, you will have 2 secant theta in the denominator. So x plus 3 squared plus 4, take the square root of this, we have 2 secant theta. And from here, dx, derivatives of both sides of the equation, so we just have dx on the left-hand side. On the right-hand side, we have 2 secant squared theta, d theta. Therefore, this integral now becomes the dx, it's 2 secant squared theta d theta. On the denominator, we just have 2 secant theta. Okay, this simplifies to integral of secant theta d theta. And this will be ln absolute value of secant theta plus tangent theta plus c. Secant theta, you can get it from here. You divide by 2. Tangent theta, you can get it from here. Again, divide by 2. So that we will have the final answer as ln absolute value of x plus 3 squared plus 4. Take the square root of this divided by 2. And by the way, for this one, you can write it as this one, since they're the same, right? Then tangent theta, it's x plus 3 over 2. And then the arbitrary constancy. So this is the final answer. Okay. This last example, I will leave it to you, and of course, you need completing the square in order to solve this before doing your trig substitution. So I'll leave this one as a practice. Right? But in place of this example, I would like to do another example because for this one, this particular example, we will need this in our next topic. So in here, I want the integral of x squared plus a squared. In here, we assume that let a be greater than 0. We assume a greater than 0. So this is the second form. Particularly, we use tangent substitution. So we will have here x is equal to a tangent theta x squared. This is a squared tangent squared theta, and we will have x squared plus a squared equals a tangent, or a squared tangent squared theta plus a squared, or this becomes a squared secant squared theta. And we don't need to get the square root because we just need x squared plus a squared. From here, we have here dx equals a secant squared theta d theta. Therefore, we will have the integral of a secant squared theta d theta in the numerator. On the denominator, you will have a squared secant squared theta. And this simplifies into 1 over a integral of d theta. And this one equals 1 over a theta plus the arbitrary constant c. But from this expression here, we will have tangent theta equals x over a, or theta equals arctan of x over a, which means the final answer here will be 1 over a arctan of x over a plus c. So I want you to memorize the formula because it will be helpful in the future, and particularly in our next topic. So integral of dx over x squared plus a squared. This is 1 over a arctan of x over a plus c. Okay, so that's all from me for this video, and I'll see you on the next one.